This is our second problem for isometric processes. Kindly take your time to read and understand the problem. The working fluid in this problem is oxygen. The, the initial pressure inside the tank is given, and it is stated that 300 kilojoules of heat is added per kilogram of oxygen. Therefore, we denote this information in our given as small letter q, and its sign should be positive. The storage tank in the problem corresponds to a rigid container. Therefore, we can say that the process undergone by the gas is an isometric heat addition process. Lastly, the temperature at the end of the heat addition process is given to be equal to 1000 Kelvin. From this given information, we shall compute the following quantities. Now, since this problem is the same as the previous problem, in the sense that both gases undergo isometric heat addition, then the PV and TS diagrams for this problem are also the same as the previous one. We first compute for the initial temperature of the gas. We can find its value using the formula for finding the amount of heat transferred per unit mass. But since we are instructed to use exact solution, then we cannot consider the specific heat at constant volume to be constant. Therefore, we shall equate Q to be equal to the change in specific internal energy, which is just equal to the final specific internal energy minus the initial specific internal energy. We can get the values of U sub 2 and U sub 1 from the appendix A19. However, if you look at this table, this will not give you the values of the specific internal energy. Rather, it will give you the values of the internal energy on a per unit mole basis, which you can see right here. So for us to get the values of the final specific internal energy, we divide the U bar value corresponding to 1000 Kelvin in the table by the molecular weight of oxygen. The internal energy per unit mole of oxygen at 1000 Kelvin is given to be equal to 23,075 kilojoules per kilomole. Therefore, dividing this value by the molecular weight of oxygen, we will get 721 kilojoules per kilogram as the value of U sub 2. Now, for us to get the value of the initial temperature, we will be basing it on the value of the initial specific internal energy. So by rearranging the formula above to isolate U sub 1 at the left side of the equation, we will be able to get the initial specific internal energy. Now we shall convert this value to internal energy per unit mole, since the U values listed in appendix A19 are expressed on a per unit mole basis. So by multiplying U sub 1 by the molecular weight of oxygen, we will get the initial internal energy per unit mole of oxygen. Now we use the value of the U over bar sub 1 to interpolate the value of the initial temperature T1. If you go back to appendix A19, you will see that this value lies between 13,417, which corresponds to 620 Kelvin, and 30,657, which lies at 630 Kelvin, or which corresponds to 630 Kelvin. Therefore, by interpolating T1 between these values, we will get 622.4 Kelvin as our final temperature. Now, before we proceed, I would like everyone to try solving for T1 using approximate solution. What you will get is 543.9 Kelvin. Now you may ask, why is the difference quite high? The reason behind this is that the temperatures involved in this problem are far from 300 Kelvin. Remember that the specific heat ratio of oxygen is equal to 1.399, and this is equivalent or this is evaluated at 300 Kelvin. This means that as the temperature of the gas gets farther and farther from 300 Kelvin, the less accurate will be the answer that we are going to get from using approximate solution. Next, we will compute for the final pressure P2. To compute for P2, we can use the PVT relationship for isometric processes. By isolating P2 at the left side of the equation, we will get 1365 kilopascals as our final pressure. Lastly, we will now compute for the change in specific entropy. Again, since Appendix A19 does not list values for the specific entropy of oxygen, then we will compute for it using the change in entropy per unit mole divided by the molecular weight of oxygen. From Appendix A19, the final entropy per unit mole is 243.4 kilojoules per kilomole Kelvin. But for the initial entropy per unit mole, we shall be interpolating its value since the initial temperature 622.4 is not listed in Appendix A19. Now, based on Appendix A19, we know that the value of S naught sub 1 over bar is between 227.4 and 227.98 or 918, which corresponds to the two temperatures 620 and 630 Kelvin respectively. Therefore, by interpolation, we will get 227.5 kilojoules per kilomole Kelvin as the initial S naught sub 1. Finally, substituting all the known values in the formula for delta S, we will get 0.37 kilojoules per kilogram Kelvin as the change in specific entropy in this example.